Okay, so we'll move on here, continue on here in chapter 2. And this is all about descriptive statistics. And the idea with descriptive statistics is that we are trying to take an entire set of data and summarize it with just a few key facts. Okay, so we want to take, lots of data with a few key facts. Okay, and so, like any other summarizing job, this is a difficult thing to do. If I were to ask you, and I'd say, on a piece of paper, write down, summarize, tell me who you are in 3 sentences, everybody would have a different idea of what they should bring up, right? Some people will say, talk about their career, and other people will talk about, great passions in their life, or other people will say, mention their, ethnic background, and where others people will say, this isn't important. And so, trying to take a bunch of data and describe it with just a few numbers is also presents a challenge. And so, there are a few values that, or a few what we call summary statistics that we use that are kind of agreed upon as these are good things, these are good ways to summarize things, but they may not necessarily be the best way to summarize things in all situations. Okay, and the way we summarize data depends on the kind of data we have. Okay, so we will cover what we call summary statistics, okay, which are quote unquote key values that can summarize a data set. Okay, data set can also be just thought of as a sample of data. Okay, whenever I say data set, you can just think sample of data. So not the entire population, again, a sample of data. And which summary statistics we use depend on the data we have. Okay, and the greatest advantage, or the great benefit that summary statistics offer us, is that they allow us to make comparisons from one sample or one data set to another data set easily. Okay, so the benefit of summary statistics is that we are able to comparisons between groups. The Dodgers, I think their magic number is now 4, if anybody cares. Meaning they have 4 wins and they will be guaranteed a spot in the postseason of baseball. The Los Angeles baseball team. All right. Okay. So I just heard the ESPN chime. So yeah. So that's what summary statistics do. Okay. So if we're talking about sports, and you get 2 people in a bar or whatever arguing about who is the greatest baseball player of all time or whatever, they'll probably start bringing up summary statistics of a person's baseball career or whatever it might be. They might say so-and-so had this batting average, okay? And they'll say, this, or they hit this many home runs or something. They're trying to summarize a person's entire baseball career, however many years of baseball this person played, and they're trying to summarize it with a single number and saying, see, look at this number. This number is this compared to this other person's number, or the average number, which is this. Therefore, this person is special. And how is there merit in that argument? Yes, there is some, but it's also hard to judge someone entirely on a single number. For those of you who are applying to graduate programs, you're probably looking at your GPA and you're saying, oh, I wish my GPA was this, or I hope they don't look down on me because my GPA is this, or whatever, or you think, I've got a good chance because it's this. And essentially what that single number is supposed to do, or it tries to do, is it's trying to sum up your entire academic performance into a single number, okay? And does it do a good job? Kind of, I guess, Obviously, a student with a 4.0 GPA probably is a better student than the student with a 2.0 GPA. But is the student with a 3.7 better than the one with a 3.5? That's, it's a lot more nuanced than that in terms of how do you define what a good student is? How does this one number capture a lot of details, right? Did this person just take easy classes, or did this person, have to work 3 jobs to support him or herself through college? Lots of things. It's hard to capture things with a single number. However, if you need to look at hundreds of applicants or thousands of applicants and just try to kind of whittle away the stacks, the GPA could serve as a useful tool in separating certain piles. But to live and die by a single number is not recommended for anybody in life, right? So I think because summary statistics allow us to make comparisons between groups, it also allows us to, quote, be lazy and just look at a single number or a few numbers and just make decisions. It's also easy to come up with rules and say, well, look, this is this number and we're going to cut it off here. And life is probably more complicated than that. But anyway, we've got to cover all of this. So, which summary statistics we use depend on the data we have. Okay, and so data can be thought of as in 2 categories. We've got numeric data, or numeric variables, also known as quantitative data. And we have categorical data, also called qualitative data. Okay. So numeric data tells us how much, how many Categorical tell us what type or what kind, or can also serve as a label. So numeric, things that are numeric: weight, height, age in years. These are all numeric. Categorical, we can have hair color, maybe race, or we can also have age, but if we categorize them as adult versus minor. Okay, so a lot of times, so certain things, certain variables can be numeric if you are measuring it in terms of a how much or how many, but you can also use the same variable and turn it into a category, right? So in America, it's an arbitrary number, but that's the number we use. We say at age 18, you are considered an adult. You can vote, you can buy a gun, you can smoke and play the lotto. If you're 17 and 364 days old, you cannot do any of these things. So that is that's that. Okay. The book further divides numeric data into continuous versus discrete. Continuous meaning you can take on decimals, and discrete means only certain values are allowed. So I'll throw that in here. And then with categorical data, there's other, you've got nominal and ordinal, but it doesn't really matter. Okay, these are the two broad categories: numeric versus categorical. So let's talk about summary statistics first for categorical data. Okay. Okay, so for categorical data, we will have counts and frequencies, and percentages. Okay, so if you think of your, let's say we looked at flowers. Here, just some raw data. I looked at 100 flowers, and I just wrote down what color they were. So I got a red flower, and I got a white flower, and a pink flower, and a red flower, another red flower, and another white, and another pink, and another pink, etc., etc., etc. So this would be red, white, pink, so on and so forth. Okay, and I can summarize this with a frequency table. So I would have the color, and I would have red, white, pink, and I'm just completely making up numbers here. 42 and 46 and 85. Okay, so these would be the counts or frequency. Count and frequency are interchangeable. And then we might have relative frequency, which then turns these into percentages. So I would say I would do 42 plus 46 plus 85, and I get a total of 173 over here. And then so to get the relative frequency, I would do 42 divided by 173. And I get 0.243. And doing the same for the other ones. And then I can create a bar chart of each of these colors. I've got red, white, and pink. And I can do I can plot the proportions. And so red comes up to 26. Oh, I'm sorry, 24. So that's like down here. This is not very good. Or something like that, okay? And that's what we've got, okay? So this is a bar chart, and this is called a frequency table. Is that okay? And that works for categorical data. We'll come back to categorical data like in several chapters, but this is pretty much it. There also pie charts exist, but we don't like those. Okay. Questions?
Why don't you like pie charts?
Because our eyes are very bad at distinguishing angles. Okay, so if I had this piece of pie, and this piece of pie, and this piece of pie, and I said which piece of pie is the biggest and which one's the smallest, you couldn't do this with any degree of confidence. Okay, but over here, if I had this and this and this, I could ask which bar is the tallest and which bar is shorter and things like that. Your eyes are much better at distinguishing heights there, okay?
It's 24 and 26. They look the same.
What's that? My 24 and 26? I would argue this one looks a tiny bit taller. We'll check the line there or something, but yeah, okay. But maybe on the projected screen. On my screen it looks pretty, yeah, I figured, okay. All right, so anyway, okay, let's talk about numeric data, okay, and their summaries. So we can also have frequency distributions for numbers, okay? So you could imagine gathering a bunch of data here. Let me do this. So you don't have to copy this. This is just in your textbook. All right, so here I've got, we went and we took cholesterol numbers for 36 different people, okay? 36 different men. And these are just the raw numbers, 36 people, here they are listed, okay? And then we created a frequency distribution. We said, oh, okay, we created some bins, and we said, how many men have cholesterol levels from 20 up to, but not including 40, so basically 20 to 39.99, okay? And we look here and we go, oh, here's one guy with a cholesterol level of 25, and that's him right there, okay? How many people have cholesterol levels between 40 and 59.999? So we look through and let's let's circle these. I got 42, 48, and I'm scanning 57 and 58. Okay, so we have 4 guys right there. Okay, and we can do that for every single bin and count, you know, who is who. And so at the end of the day, if there's 36 numbers here, we're going to have a total of 36 people here, and this is our frequency table. Is this the creation of this? Okay. All right. So this is you know, from 20 up to, and then we would then draw this as a histogram. And actually, let me just flip the page and use the one that they've already drawn for us, rather than me trying to draw a junky version of a histogram here. Okay, so after they've created the frequency table, we can then, I did this poorly. We can then do this. Okay, and so if we look right here, between 20 and 40, we have you know, little our axis. So along our x-axis, we have the cholesterol level. Okay, our CK concentration right here, and that goes from 20 to 40 to 60 to 80, you know, so on and so forth. And so this bar has a height of 1. Okay, and this is this one guy here. And to show that there were 4 people with cholesterol levels between 40 and 59.9, we have a bar going from 40 to 60 with a height of 4. Okay, and our graph ends up looking like this. Okay, when we create this graph is called a histogram. It is not the same thing as a bar chart. Okay, bar charts are for what kind of data? For categorical. So if I flip up the page, we have a bar chart. This is categorical. You know, stylistically, we usually put spaces in between the bars here, and the ordering of the bars is arbitrary. Okay, I could have arranged them pink, red, white, or pink, white, red. I could arrange these orders however the bars however I want, and that's fine. So with bar charts, order of the bars or arrangement is arbitrary. Over here, I can't rearrange the bars because the bars are associated or tied to the number line, and so there's no number line where 40 to 60 comes before 20 to 40, or, you know, I can't move this bar over here because that would change the number line. So with histograms, the order of bars is fixed, and because of that, we can then start talking about the shape of the histogram. Okay, and so on this side, we call this the right quote-unquote tail, and over here would be the left tail, and then and the peak is called the mode. All right, and you know, it would not make sense to talk about left tail and right tail for a bar chart when you can just mix around the order of bars and create whatever shape you wanted to create that way. Okay, but with a histogram, you can't make whatever shape you want. The shape you have is the shape you get, and so you have we can talk about left tails and right tails and the shape of the distributions. Okay, and so when we're talking about distributions, here, actually, let me yeah, I'll draw these out. Okay, and This is not very good. Okay, we can get something like this. We can get something like this. Or we can have something like that. Okay, and so over here, our left tail and right tail are supposed to be the same size, and we would call this symmetric. Okay, and we have one peak, so we would also say it's unimodal. Okay, both tails same size. Over here, so underlying this, basically, maybe I didn't make this clear. I'm essentially just representing the histogram with a curve. Okay, so rather than drawing out every single bar, I'm just representing a histogram with kind of a smooth curve. So over here, what do I have? Do I have a left tail or do I have a right tail on this upper one here? I have a left tail, right? So I've got a long left tail. I should do this in another color. And I hardly have no right tail. Okay? So what does this mean? And over here I've got long right tail. And, you know, hardly any left tail. Okay, so, you know, what does this mean? Okay, well, let me apply labels to these. This one is called right skewed. And this one is called left skewed. But what does it mean to be right skewed and left skewed? Over here it means we've got some values. If we're talking about a right skewed distribution, we've got some values that are much larger than the mode or the peak, or this would be kind of the most common values, right? The mode is what is most common. So we have some values much larger than that, and we hardly have anyone that's much, much smaller than that. Okay, and actually if we tried to go out the same distance, you know, if we said if the, you know, the mode is right here and we go out this distance this way, we have nobody down here. Okay, and then just the opposite applies over here. So can you think of numeric data that might be left skewed or right skewed? Age? Okay. Age. Yeah, age I would not say is neither left nor right skewed. It follows a funny distribution.
Unless you said like age of residents in a nursing home.
Yeah.
Housing prices across the country.
Yeah. Okay, so price things. Yeah, so housing prices or even just income. Income is very heavily right skewed, okay? Most Americans probably make between, just broadly speaking, $40,000 and $100,000, okay, per year. Most, or 30, we'll say 30 to 100,000, okay, and that's going to cover the bulk of America. Are there people making $1 million a year? Yes. Okay. So let's say the average is like 50,000. Okay, and 1 million is what? Is 950,000 more than average. Okay. If we were to go 950,000 less than average, where would that take us? That would take us to negative $900,000 per year. Is there any wage that pays negative 900,000? That would be a, I don't know. Yeah, there's no job that pays that, you know. So we have some, income is very right skewed, okay? You have people making $1 million a year or even more, which is, literally, $1 million is literally 20 times more than 50,000 or 950,000 more than something around the average of 50. And you've got no one making that much less, right? It's like impossible to make less than zero as a wage. Maybe you've made some bad investments and you're perpetually falling in debt, but in terms of a career or job, you don't get paid a negative wage. I guess Steve Jobs took a $1 salary one year or something, so he would show up right over here, but really his actual income is probably over here. So yeah, whatever. So we've got a long right tail, and over here for left skewed means it's impossible to be above this, but you've got a lot much lower. So this might be scores on an easy exam where you've got the bulk of students getting 90 to 100%, but not possible to get over 100%, and maybe you have a few students getting 30% or something like that if they're poor. Okay, so that's those are shapes of distributions. All of these would be classified as unimodal because they all have one peak, so these are all unimodal as well. And so we could have other distributions that maybe look like this, and this would be bimodal. And if you have anything more than that, we might just call it multimodal. So can you guys think of a variable that might be bimodal? Okay, and so with bimodal, remember we have to talk about a numeric variable. Okay, so a lot of things, you might think of things that show up in two categories, but that would not count because the shapes of distributions apply only to numeric variables. So so something that might be bimodal or is bimodal would be testosterone levels. Okay, so every person produces testosterone in their body. Okay, but in general, well, not in general, as a fact, men produce more testosterone in their bodies than women do. Okay, but women still produce testosterone. And so if we were to measure all of the testosterone levels in different people, this would be kind of like the average testosterone level for males. Some males produce more testosterone than others, and some males produce less testosterone than others, but overall, average like this. But even, men who produce less testosterone than other men will produce more testosterone than most women. And so over here you would have kind of a peak showing the average testosterone levels for women. And so, someone over here would either be a woman with high testosterone or a man with low testosterone, okay? And then down here would be women with lower testosterone than other women. So, but you would see this kind of bimodal nature here. Okay, does that make sense? So something like that. If we were to look at if there was some number that we could apply to political opinions, okay, like, and this is a very tricky thing to do, but if somebody could rate your, let's say there was a conservatism score, right? So if you are very conservative, you would score 100, and if you are very liberal, you would score 0. Okay, and I know there's all sorts of faults with this this setup because it's not just a one-dimensional thing, But if we were to then look at people across the nation, whether you are liberal or conservative, or do you score 0 to 100, probably you would get maybe not something looking like this, but just maybe something that's not as crazy, okay, over here. Whereas when you go into, say, Congress, you probably get something a little bit more dichotomized, okay, and that's just what happens sometimes, right? So, depending on what group you have. Okay, so anyway, but I suspect that most of the nation, not most, but a lot of the nation is not as dichotomized as. This is like my second reference to Congress today. I don't normally talk about politics as much. Okay, so we have that. Let's talk about just a few summary things. Okay, so we have measures of center. We have the mean, and we have the median. Okay, we've already talked about the mode being the peak in our data, and we have the mean and the median. Okay, so conceptually, the mean, you can think of this as the balance point in our data. So if I had the values 1, 2, 3, and 10, okay, and I put these on a number line, and I got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's say I just imagine putting stones here at 1, 2, 3, and 10. Where would I need to put, and I were to balance this on a seesaw, where would I need to put the fulcrum so the thing stays balanced? And we would put it, well, not at 8, but I would do 1 plus 2 plus 3 plus 10, and I divide by 4. The place where it's balanced would be the mean, okay? And so this thing is balanced here at 4, and our mean is equal to 4. And I think you guys all know how to calculate the mean. The symbol for mean is y bar, and you add up each of the data points, add up the 4 values of y that you have, you divide by how many you have, n, and you get y bar. So in our case, we do 1 plus 2 plus 3 plus 10, and we divide by 4, and we get 16 over 4 equal to 4. So I went through that quickly, but I think you guys are all familiar with calculating the mean, right? Yeah. And then, but the concept is that it's the balancing point of our data, okay? Because if we were to look at this, you only have one data point that's larger than 4, okay? The median, on the other hand, is the halfway point in our data. So here, with the median, half of the data is larger, and half is smaller than the median. So in our case, if we look at the data points 1, 2, 3, and 10, the median, we would say, okay, well, I've got 4 data points, so I want the spot where 2 are bigger and 2 are smaller, okay? And so I look at these two numbers, 2 and 3, and I say, okay, well, what's halfway in between 2 and 3? 2.5. Okay, and so here my median is 2.5, which I got by doing 2 plus 3 divided by 2. And I can say half of our data points are greater than 2.5, and half of data points less than 2.5. And so we have the mean and the median there, okay? So a key thing to note,
Is there a symbol for median?
it's not a universally agreed upon symbol. You've got this as a possible symbol. Y bar is like universal for the mean. Symbol for the median, sometimes this, sometimes other things, okay? So you don't have a... So we usually just say median, or maybe you'll just call it the 50th percentile or something like that. Okay. All right. The key, a key aspect to note is that the median is not affected by outliers where the mean is. Okay. And this this plays major, has significant implications, okay? So an example could be, you know, let's say you are in a diner at a small, I don't know, small mining town, okay? West Virginia or something, okay? And then, and so you got 10 people in the diner. All of them are coal miners, and you want to ask, you know, what's the average income in the diner, okay? And let's say all 10 of them make $65,000 a year, okay? So there, the mean would be 65,000 because you add up all 10 people and then you divide by 10, you get 65,000. The median would also be 65,000, okay? Can you guys picture this so far? Okay. Let's say Bill Gates walks into the diner, okay? And I have no idea how much Bill Gates makes per year. Let's say he makes 10 million a year. Okay, he might make more or less, whatever. Okay, what is now the average income in the diner?
It's going up a lot.
Yeah. Okay. So let's just, for simplicity's sake, let's say there were, what did I say? Let's say there were 9 people in the diner, okay? So 9 people in the diner, Bill Gates walks in, he makes 10 million a year, okay? So if we just take Bill Gates' income, 10 million plus whatever pocket change these miners make, and we divide by 10, the average income for the mean would be over $1 million per person, okay? Whereas the median would still be 65,000 a year. Okay, which is a better number to summarize the income in the diner? Well, okay, so you guys seem to have said the median, and probably if somebody said, well, what's the typical income, maybe the median is a good thing to say, but the truth is in a situation like that, one single number probably doesn't very well describe what is happening in the diner, and you'd probably need to explain yourself and say, well, you got 9 coal miners and Bill Gates, or something like that. And you know, that's a silly example, but you've got more complicated data, and then you know you're trying to summarize it with a single number, and it's hard to often pick which number is better or worse, okay? And they both serve different jobs, and you got to know which one is appropriate, okay? You know, so maybe in that case, I would agree with you. The median might be a better example of what's a typical payment. If you were an insurance company, okay, and you wanted to say, well, what's the typical payout that I would have to make on a paying customer, right? Let's say you have your auto insurance company, okay? Most of your customers will not get into an accident during the year. So the amount you as the insurance company has to pay out is going to be $0, right? And so let's say 90% of your customers get into no accident. You have $0 payouts, okay? And so your median would be $0. Would that be a good number to base your premiums on? No, because it only, these other 10% of drivers that are getting into accidents, you might have someone who has, a $300,000 payout because, they cause bodily harm and all sorts of things. All of these other safe drivers basically have to pay for to balance out what's going there. Okay, so you're in that situation, the mean is a much better number to use. So anyway, measures the center, the mean, and the median. I think you guys know how to calculate these things. The book goes into detail on finding the mean and the median. I'll leave that to you in your reading and homework to do that. There's also, in the book creates a tool. It's a graphic tool called the box plot, okay? And the box plot is based on kind of like a 5-number summary, okay? It's, the box is defined. Here, let me just draw what a box plot kind of looks like. The box plot kind of looks like this. Okay, and so you have the box, and these are called whiskers. This is the box. This would be a whisker. And these are outliers. Okay, and the box is defined by 3 values. You have Q1, Q2, which is the same thing as the median, and you have Q3. Q1 is the first quartile. Also equivalent to the 25th percentile. And what this means is that 25% of the data is smaller than Q1. Okay, Q2, the median, you know this. This is the 50th percentile. 50%, or half of the data, is smaller. And with Q3, what do you think this is called? Third quartile, 75th percentile, 75%, or 3/4 of the data is less than Q3, okay? So how do we find Q1 and Q3? Well, essentially you find the median, and where you have the median, that's going to split your data in half. So you're going to end up with 2 halves, and then you split those in half again. Okay, so if you take the upper half and you split that in half, then you've got the upper quartile, or Q3, and you take the smaller half, you split that in half, you'll get the lower quartile, or Q1. Okay, and again, I'll leave it to you in the exercises and the reading to figure this out. If you get stuck, I've got kind of homework video to help you out. Let's talk about these whiskers. Okay, the whiskers extend to the largest and smallest points in the data that is, quote, within the fences. It's not a quote, that is within the fences, okay? And what the fences are these arbitrary lines that distinguish what is an outlier and what is not, okay? There are several methods for determining what an outlier is and what is not an outlier. I'll just teach you one simple method, and this is the 1.5 IQR method, okay? So, let me just write this. Fences are lines, or I guess are hidden lines, I should say, that distinguish outliers from the rest of the data. Okay, and so we could have outliers that are far too big. We can also have outliers that are far too small. In this picture, we only have outliers that are far too big. Okay. And so we have an upper fence and a lower fence. And this is just one rule for creating fences or distinguishing outliers. There are several different methods, but here we're going to say the upper fence is the third quartile plus 1.5 times the IQR. And the lower fence is Q1 minus 1.5 times the IQR. And what is the IQR? The IQR is known as the interquartile range. And it is the difference between Q3 and Q1. It is the difference between the 75th percentile and the middle 25th and the 25th percentile. Okay, this could also be thought of as the range of the middle 50%. And that is the upper fence and the lower fence. So essentially, what we're doing, the width of this box, the box goes from Q1 and Q3, and so the width of the box is the IQR. And what the upper fence and lower fence says is, okay, I'm going to take this distance, and I'm going to go 1.5 times out this distance. So say this is the width of the box, so I can, pretend to go, here's 1, and then I'm going to multiply this, this is 2 boxes out, but if I'm only going to go out half of this, and so this is, quote, 1 box, and then this would be half of the box, and so I draw kind of a line here, and this would be my upper fence. Does that make sense? And I do the same thing going the other direction. Okay. In this picture I drew, the median happened to be in the middle of the box. It's not necessarily in the middle of the box. Okay. Depending on the type of data, your median could end up over here or end up over there as well. It's just where the 25th percentile is, 50th percentile, and 75th percentile. Question? Yes.
I thought that the whiskers had to be within the fences.
Yeah, they are within the fences. Yes.
Oh, sorry. I thought that line that you drew was.
Yeah, so all I'm saying is, so this line here is saying I'm going out 1.5 boxes above Q3, okay, or 1.5 times the IQR, which is the width of the box, and then I could do the same thing over here, and I'd probably end up over here for the lower fence. Okay, and so the whisker goes to the biggest point in your data that's not an outlier, essentially. Okay, so it doesn't go necessarily to the upper fence. It's just if this is the biggest point that's not considered an outlier, the whisker goes out to there. Okay, the book calls this a modified box plot, or box plot with data for outliers, or something like that. Pretty much every other textbook that you read will call this just the regular old box plot. So, so you have that. And you know, we don't create box plots just for fun. Okay, the purpose of creating these box plots, just like everything else with these summary statistics, is it allows us to make comparisons between groups in kind of a quick fashion here. Okay, and so let me just see if I can find some box plots. So for example, in this diagram, I've got 4 data sets, or actually in the exercise, we're trying to match which one goes with which. But here I've got 4 different data sets, and I've got 4 box plots. And from this we can see all sorts of things, right? So we can see this one has the highest median. Okay, but if we look at the range of values themselves, okay, the range being, you know, the difference between the min and the max. It's actually max minus the min. We can see they all have about the same range, right? A, C, and D have the same range, okay? Okay. Which box has the largest IQR? C, right? This one also has the largest IQR. And B would have the smallest IQR. Now, why do we care about the IQR? Let's talk about that, okay? But, you know, so with box plots, we can see this. And here we can see that the 75th percentile of A is, you know, right around the 50th percentile of group B, okay? And that's lower than, you know, the 50th percentile of group C. So you get an idea, right? The you know, if these were like student test scores or something, you know, the student in your upper, you know, the top 25th percentile student, you know, in school A is below average for school C, okay, or is right at average for school B. Okay, and so you can make these kind of comparisons very quickly with a box plot without needing to, you know, ask for the full data set and doing an analysis that way. I don't know. Does that kind of work? Okay, so that's box plots, and you know, with the little bits of time left, let me just talk about, you know, so I mentioned the range and the IQR. And so with our last bit, I want to just talk about measures of spread or dispersion. So when we're summarizing data sets into single numbers, one, we can summarize kind of the central location, and that was with the mean and the median, or the mode if you want to talk about what's most common. Spread, on the other hand, talks about, are the numbers similar to each other, or are they vastly different? Okay, so an example I use is, just think of Olympic athletes, okay, like at the Summer Olympic Games, and think of just the different athletes that you might see. Okay, and these are all people who are probably very physically fit. But you're going to see a wide range. Okay, if we're just looking at the the weight of the different athletes at the Summer Olympic Games, you're going to have people under 100 pounds, probably some gymnasts who are very strong, muscular, and physically fit, but also very small. So maybe, 100 pounds or, just around there, okay? And then you'll have, different, the swimmers will be, very muscular and probably a lot larger. Volleyball players will be very tall. If you look at the heights, you're going to see just a wide discrepancy of people, right, in terms of the values you're going to see. Contrast that to maybe cheerleaders for a football team or something like that, okay? Professional cheerleaders or cheerleaders for a pro sports team. You're probably not going to see as much of a range, okay? And I don't know if they've promoted diversity among cheerleaders and pro sports teams, but you're not going to have people who are extremely short or extremely tall, and regarding weight, you're not going to have people who are probably above a certain weight or things like that. And so the range of values that you will see for height and weight for cheerleaders is going to be much more constrained versus Olympic athletes, okay? Or any other group. You can think of different groups, and in some places you're gonna see a lot of maybe consistency in values, and other places you're gonna see a large range. And so measures of spread and dispersion assign a number to that concept of lots of spread or little spread, okay? So lots of spread mean the values, so we're still dealing with numeric variables, by the way. Values are quite different from one another. Okay, so think, weights of Olympic athletes. Some have low weight, some have high weight. Okay. Low spread means the values are quite similar to each other. So probably think of weights of, pro sports cheerleaders. Okay. Most will be around the same weight. Okay, and so the range and the IQR and the standard deviation these are all measures of spread. Okay, so they assign a value, a number, to this concept of spread. I might go a couple minutes up past 10, and I apologize. Is this okay? Can I go to the next slide here? Okay, so they each assign a value to this concept of spread, and just like the mean and the median assign a value to the idea of center, but highlight different aspects, each of these things highlight different aspects as well. Okay, so the range just tells us the difference between the extreme points. So this will be greatly affected by outliers. And maybe that's what we want. Maybe it's not. Okay? The IQR tells us the difference between the top quarter and the bottom quarter. So it's, IQR is Q3 minus Q1, okay? So this one is not affected by outliers. Okay, so the IQR, the range would kind of tell us the discrepancy between the very rich and the very poor. The IQR would kind of tell us the range of the middle class, per se, okay? The middle 50%, what is, someone in the top end of the middle 50% and the bottom end of the middle 50%, how different are they? The standard deviation okay, this tells us, this can be thought of as, well, the standard deviation, let's think of this as the square root of the variation of the quantity, the variation, okay? And the variation is the, quote, average distance from the mean squared. Okay, and the standard deviation would just then be the square root of this average distance from the mean squared. Okay, so what do we mean by that? Okay, let me just take these values 1, 2, 3, and 10 again. Okay, so we here found that the mean was equal to 4, right? Okay, so we could ask, I'm going to put dots here again at 1, 2, 3, and 10. Okay, so I'm going to draw a line at 4. This is the mean. Okay, and we ask, how far is 3 from the mean? This is 1 unit away, right? How far is 2 from the mean? This guy is 2 units away. And how far is 1 from the mean? He's 3 units away from the mean, okay? And how far is 10 from the mean? This guy is 6, okay? So rather than taking the average of these, we're going to square each of these things, okay? So we square that distance from the mean, and we get 3 squared plus 2 squared plus 1 squared plus 6 squared, and I get 9 plus 4 plus 1 plus 36, and I get a total of 50, okay? And then I would take kind of the average of this, and I would divide. You'd think we divide by 4, but we divide by 3, okay? And that's why I put average in quotes. And so, we divide by n minus 1 and not n. Okay, and if you want to know why, this is called Bessel's correction. To get an unbiased estimator, but we don't, it doesn't matter. Anyway, so we divide this by 3, and this gives us the variation. It's kind of the how far are things from the mean. Let's square that and take the average, okay? Except we divide by n minus 1 rather than n, okay? And so it kind of, it's a balance. It's kind of like it weighs out how far things are from the mean, because the idea again is how spread out are these numbers. So we're saying, well, let's think of the mean as the middle point or the balance point, and we're going to see how far are things from this quote-unquote middle point, and then and get an average value there. Okay, and that's the idea behind the variation and the standard deviation. Don't get lost in the formula or the calculations of that. I've got a video going through the details of that as you do your homework and stuff. But the main idea behind this is just remember standard deviation, IQR, and range all cover this concept of spread. Are the numbers very different from each other, or are they quite similar to each other? Okay, that's it for today. Sorry for keeping you